Hello, my name is Sejal Bankar and I'm here to explain molecular docking and lead discovery of acetylcholinesterase inhibitors for Alzheimer's disease, a computational approach to identifying the promising drug candidates. So, understanding the Alzheimer's disease. Alzheimer's is a neurodegenerative disorder and it leads to memory loss and cognitive decline over time, progressive and irreversible. It has a huge global impact and there is an urgent need for effective treatments to improve its quality of life, patients' quality of life, and focus on its early detection and therapeutic interventions. So, what is the role of acetylcholine in cognitive function? So, normally it is involved in cognitive processing, learning, memory formation, and attention. But in Alzheimer's disease, what happens? Acetylcholine decreases. The cholinergic neuron is lost and it worsens the cognitive deficits. So, now what is acetylcholinesterase? It is an enzyme which is involved in degradation of acetylcholine, and we have already looked what are the functions of acetylcholine and why it is essential. So basically now acetylcholinesterase, it acts as a potential drug target. So these are the objectives of performing the molecular docking. First of all, I'll be selecting my target protein. Then I'll prepare the protein and ligands. I'll perform docking using Pyrex software. I would analyze the interactions and further identify the promising lead compounds. So the target which I chose was 4EY7, acetylcholinesterase 4EY7. So, this crystal structure provides crucial insights, especially as it is in complex with donepezil. So, first of all, I would like to highlight in the presentation, I have just kept a theoretical part and the practical concept, but everything related to my project is being detailed in already in the Word document. So, the active site residues which were identified are enlisted below, which are tryptophan 86, tryptophan 286, tyrosine 337, histidine 447, then asparagine 74, phenylalanine 295, tyrosine 341, tyrosine 124, phenylalanine 297, and serine 203, glutamine 334, of which the catalytic triad, it consists of serine 203, histidine 447, and glutamine 334. These three are the crucial or critical residues for the enzymatic activity of acetylcholinesterase. It forms a catalytic triad, and hence these three of them acts as a potential target. So the catalytic triad plays a pivotal role in the hydrolysis of acetylcholine, and we are supposed to block it by introducing the small molecules and thus analyzing the efficiency of the small molecules to bind to this triad and inhibit this triad. So disrupting the function of these residues is a primary strategy for acetylcholinesterase inhibitors. Further, the methodology involved in protein and ligand preparation. So the protein 4EY7, first of all, its entire history was analyzed through UniProt. Its ID was pasted in RCSB PDB and the protein was downloaded in PDB format. Further, it was curated using BioVia Discovery Studio. The 10 potential ligands were tested. First of all, they were downloaded from the PubChem website in SDF format, and then they were converted into PDB QT format in Pyrex software. Further, the molecular docking was performed using the Pyrex software, where the protein was converted to PDB-QT format, ligand was converted as I said previously, then grid box generation was done. Here we are doing blind molecular docking, where we are analyzing the entire molecule along with its active site as well as the non-active sites. Further, we'll do the docking execution using Autodock Vina, which generates the docking score of several ligands. The docking which I performed it with the multiple ligands, which were 5 of them. The softwares used are Pyrex, Autodock Vina, Discovery Studio, and PLIP. Further, the docking results. So, uh, what I analyzed was donepezil has the maximum of binding affinity, which is minus 11.3, and the order decreases with the galantamine and then the rivastigmine. So these three of them are the potential drug candidates for acetylcholinesterase. So I have also given the detailed interaction analysis of the donepezil as shown below, and these are the key findings where I did the molecular docking. Then I identified the ligand, which is donepezil, having the strongest binding affinity, and further the multiple favorable interactions observed with the active site residues. So donepezil shows a promising, it is a promising candidate and a potential AChE inhibitors with this strong binding affinity for the Alzheimer's treatment. These are the future directions where it has been involved in molecular dynamics simulation to analyze protein ligand complex, its behavior, stability studies, then ADMET studies, that is studying the pharmacokinetic properties, and the experimental validation to confirm the computational findings through laboratory experiments. This is the conclusion. Thank you.